Fraud detection remains a critical challenge in the financial district, as fraudulent activities can involve abnormal transactional behaviors. Detecting outliers or anomalies in large transactional datasets is key to identifying potential fraud. This project uses unsupervised learning techniques, specifically anomaly detection via the use of a random forest to flag suspicious transactions based on the data. My name is Darwin Gomez, and this is my project, Fraud Detection in Bank Transactions. The objective of this project is to detect anomalies in bank transactions using the isolation forest algorithm. Bank transactions can exhibit suspicious patterns indicative of fraud, such as high transaction amounts or repeated login attempts. The analysis uses a dataset containing transaction details, customer information, and contextual data. Our data comes from Kaggle.com, the dataset, bank transaction dataset for fraud detection. And here are some of the variables that we'll be working with. Variables of particular interest are things like transaction amount, account balance, a customer's age, the date, transaction type, and login attempts. We start our analysis by exploring the data. First, we check for missing columns. This dataset has had some pre-processing, and so there is no missing data rows. Then we get some summary statistics. It's important to understand these summary statistics before we run our model, because that way we know things like the mean for numerical values, like account balance, transaction amount, transaction duration, login attempts, or customer age. For example, the mean of a transaction is $297. And on average, login attempts is at around 1. Channels represent where the transaction takes place, online, ATM, or branch. Since these are levels, we should probably encode this. And then we have two different types of transaction types, debit or credit, with debit being the majority. In this slide, we take a look at some visuals for some of the key variables. The box row represents box plots for login attempts, transaction amount, and account balance. A box plot shows us any potential outliers. As we can see, for login attempts, anything above 1 is considered an outlier. In the transaction amount box plot, we can consider transactions above $900 to be outliers. The distributions are all highly irregular, rightly skewed distributions, meaning that we can expect to see long right tails on all of them, and we do. Here we plotted some variables against each other. A particularly interesting one is the age versus account balance. I found it funny that the customers between ages 20 and 30, for the most part, tend to have the lowest account balance. I guess we've all been there, right? The big one on the right here, account balances versus transaction amount, is actually pretty interesting. It shows all the data points with their transactions on the y-axis and account balances on the right. As we saw earlier, we have some variables that are numeric. They have labels. And so in order to build a model using some of these variables, we would have to encode them. So in this slide, I'm showing the process for that. The next step was to convert the date columns into a numerical format that we can use to do calculations. Python presents us with date time, and so we did that. Next, we use standard scalar to standardize all our numerical data. Now, onto the model. Isolation forest is an unsupervised machine learning algorithm used in anomaly detection. It works by isolating data points through recursive random splits. Anomalies or outliers are easier to isolate because they are further away from other points and you're usually in low density regions of the data set. Anomalies are isolated with fewer splits compared to normal points. How does random forest works? It randomly selects a feature and splits a value. It partitions the data until individual points are isolated. The number of splits or the depth of the tree is needed to isolate a point is measured, and anomalies are isolated with shorter paths or fewer splits. To train our isolation forest, we first made a features list that we want to train the forest on. Then we call isolation forest and we pass the following arguments: the number estimated, which is standard at 100, and the contamination level. I also set a random state for reproducibility. The important things here are the estimators, which kind of tells the isolation forest how many decisions or splits to do before it reaches a conclusion, and B, the contamination level. So contamination level is pretty much how often or what percentage of the data we expect to be anomalies. For transactional data or bank data, it is known that only about less than 0.05% of all transactions are fraud. So for my model, I actually went a little bit above and went with a 1% contamination rate. So we expect about 1% of the entire data set to be flagged as anomalies. After running the models, the number of anomalies detected were 26. I did a quick check on transaction types to see how that formulated. And we had 16 anomalies that were credit and 10 that were debit. If you remember from earlier, this is a little off because most of our transactions were of the debit type. Maybe transaction type is a key indicator if there is an anomaly or not. In this plot, I have highlighted all the anomalies in red against the rest of the data. And we see that we do have some anomalies in higher account balances and large transaction amounts. But there are some among the big clusters here which suggests that there are many features being considered in the model. So how do we make sense of that? This next plot is a pretty cool one. We have login attempts on the left and transaction amounts on the X. And we can see here that many of these transactions that were flagged as anomaly all had over the minimum amount of login attempts. Remember that we scaled all numerical values, so even login attempts was scaled using standard scalar, and that's why we see this bottom set of points below 0. But really that's our baseline, meaning that all these points on the bottom are actually one login attempt. In this plot, I have plotted all the anomalies and only the anomalies, and I've labeled them by credit or debit just to get an idea of how they plot. And in this plot, we have that funny plot that I thought was interesting between age and account balance and plotted anomalies on top of that. As we see, the anomalies are distributed throughout the entire data set, but we definitely have a vast majority of them in the higher account balance. Analyzing the model. So how do we actually analyze what our model is doing? SHAP, or the Shapely Additive Explanations, helps us with that. SHAP provides insight into how individual features affect predictions. And SHAP can explain the overall model behavior by indicating prediction levels. The sum of the SHAP values for prediction equal the difference between the model's output and the expected output. Our SHAP call gave us the features with the highest impact on the models from top to bottom. So the most important features for our isolation FARs are login attempts, transaction type, transaction amount, and account balance. After seeing the Shapely values, I went back to the original means and summary statistics and compared them to the means of the anomalies. And what I found was this difference in means. I printed out a table here on the bottom that has the percent change in the means of all of these metrics. Transaction amount has a plus 87% change in mean, transaction duration plus 36%, login attempts plus 225%, account balance plus 54%. And then the plots on the top actually are bar graphs, with blue being in the original and anomalies being in red. As you can see, anomalies for login attempts on average are much higher than the original. The same could be said about account balance, transaction amount, and transaction duration. The goal of the project was to find unusual transactions or anomalies in bank data. Since the data didn't have labels, we used a supervised learning method to accomplish this. But before that, we had to prepare the data. We encoded categories like transaction type, location, and channel, and we standardized numerical features. We also extracted date and time data using datetime. To detect anomalies, we ran isolation FARs at a contamination rate of 0.01% based on industry knowledge that less than 1% of bank transactions are typically fraud. The model flagged 26 transactions as anomalies. To understand our model, we used Shapely additive explanations to see which features the model relied on most. After that, we compared means between the anomalies and the original data. This comparison showed that the anomalies had much higher averages for all numerical values. The isolation FARs helped us find these anomalies, and Shape showed us the features which matter most. By combining the model's results and our understanding of the data, we got a clearer picture of what makes these transactions unusual. For future studies to improve anomaly detection, we can add features like the device ID or IP address. For example, ATM locations. If An ATM is a known hotspot for suspicious activity, including the device ID, would help flag those ATMs. Similarly, through IP address tracking, if an account shows multiple login attempts from an unfamiliar IP address, this could indicate potential fraud or unauthorized access. These additional features can enhance the model's ability to detect anomalies and provide more contextual understanding for suspicious activities. This project shows that unsupervised learning can do a good job of finding outliers even when we don't have labeled data. Using tools like Shapely, like SHAP, helps us explain the model's decisions, and adding domain knowledge makes the results meaningful. Feel free to connect on GitHub or LinkedIn as we all embark on this journey of learning together.